Okay, so we're going to be looking at motors ILM, operation of three-phase induction motor. This is 302B, and in particular we are going to be looking at the rotor. And to talk about the rotor, we are first going to have to talk about some terminology. And first is the synchronous speed of a motor. So what is the synchronous speed? The synchronous speed basically comes down to it is the speed of the rotating magnetic field. So we can calculate, so here's a little picture of that. What's going on is that as each one of these phases is energized, and 120 degrees later, the next phase, it creates basically a rotating magnetic field. So we have this picture here drawn without the rotor. So we can calculate the synchronous speed of a motor by taking the frequency of our supply, multiplying it by 120, and then we divide it by the number of poles. So that would be the formula to calculate synchronous speed. So let's just run through a few examples. So if we have a 60 hertz machine times 120, that's going to work out to 7,200, and we divide it by the number of poles. So the number of poles of a motor always has to be an even number. So the lowest even number would be 2. So if we had a 2-pole motor operating at 60 hertz, we're looking at roughly 3,600 RPM. A 4-pole, its synchronous speed would be 1,800 RPM. 6-pole, 1,200. An 8-pole, 900. A 24-pole, 300 RPM. And what are some typical motor nameplate values for RPM? So 1760, which would be a 4-pole machine. 3450, that would be a 2-pole machine. 850, that'd be an 8-pole machine. 1160, well, that would be a 6-pole. And 250 RPM would be a 24-pole. So we might see RPMs such as that as on the nameplate. So that's the full load speed of the motor, and when we see that, we'll know that it's a certain number of pole motor and it's going to have a certain synchronous speed. So for example, the 3450 RPM 2-pole motor, well, from 3450 we know that that must be a 2-pole, and its synchronous speed, or the speed of the rotating magnetic field, will be 3,600 RPM. Yeah. So moving on, if we had 50 hertz machines, so this is European frequency, so it's still the same thing, the synchronous speed, same formula, frequency times 120 over the number of poles, and so be 6,000, so 50 times 120, 6,000 divided by the number of poles. We're going to see a little bit different synchronous speeds on each one of these motors, or speed of the rotating magnetic field. Nameplate values might be something like this. So the RPM has always got to be slower. The actual full load RPM has always got to be slower than the synchronous speed. You can never be as fast as it, otherwise it wouldn't be an induction motor anymore. We would have something called a synchronous motor. So we're going to dive a little bit closer into the induction motor and what's happening in that rotor. And to do this, we've got to look at some rotor parameters. And just to define a little bit some of the terminology that we're using. So rotor speed. So rotor speed would be the actual speed that the rotor is turning at whichever point in time. So the rotor is connected to the shaft, and so in our picture here on the right, it's the gray part, and the rotor bars here are in red on your right. So rotor speed, how fast it's going. Rotor slip. Now, what is rotor slip? Well, rotor slip, from our previous example, we had the synchronous speed of our machine, so N synchronous. Okay, and so if I subtract off the actual speed of the rotor, so this would be the rotating magnetic field, the speed of the rotating magnetic field, and I subtract off the actual speed our rotor is going, we call that the slip, or rotor slip. Okay, slip. All right, so the slip of a motor is your synchronous speed, subtract the actual speed of the rotor, or the RPM the rotor is going. Rotor voltage. Well, when we have a magnetic field that's rotating at a constant speed, like our synchronous speed, and then the rotor sitting there in the middle, what's going to happen is we induce a voltage on that rotor. And as that starts to speed up, that rotor voltage begins to change. It doesn't get cut at the same rate anymore. So the rotor voltage, we say it's a blocked rotor, means the rotor is not moving, or 100% slip. And so it's not moving. And so we'll get our maximum induced voltage at blocked rotor values. As that starts to speed up, the rotor starts to accelerate. Now the rotor is not getting cut as fast, and the slip starts to decrease. So the induced voltage on the rotor starts to decrease as well. Once we have an induced voltage on that rotor, current's going to start to flow. So it'll flow through these rotor bars, go through the end rings, come back on the other side, and back through the end ring on this side. So it's basically like a short-circuited transformer. And at blocked rotor, if I were to block that rotor and not allow it to move and turn the supply voltage on that stator to create the rotating magnetic field, it's just like having a short-circuited secondary transformer. So what dictates, once we get the voltage across induced on each one of these rotor bars, we have some opposition to current flow. And one is the resistance of those rotor bars. So that's fixed no matter what, as long as we're looking at a standard squirrel cage induction motor. We're going to talk a little later about a wound rotor. That one we have the ability to vary the resistance in the rotor. Because these rotor bars are surrounded by metal, or basically a core material, they also have rotor reactance. So we have opposition to the current flow through those rotor bars based off of the XL of that. Now, if you recall XL, the formula for it is 2 pi FL. All right. And so as this rotor starts to catch up, we would have, at blocked rotor, we'd have our maximum frequency. So that'd be the frequency of the induced voltage. So frequency, if this was a 60 hertz motor and this rotor was blocked, we would have a full 60 hertz at blocked rotor of induced voltage on it. But now as it starts to accelerate, the lines of flux aren't cutting it as quickly anymore. So the frequency of that induced voltage on a rotor starts to drop. So because the frequency of our induced voltage is dropping, well, that affects our reactance. So as it speeds up, the reactance starts to decrease. And it decreases in proportion to the percent slip. So both of these will combine at these different speeds the rotor's going to create the overall or total opposition to current flow within the rotor. That's the rotor impedance. Formula for the impedance is just like we did several times already. It's the resistance, in this case, of the rotor squared plus, which is fixed, plus the XL of the rotor of whatever the reactance is at that speed, squared. And so we can calculate the rotor impedance. Now if I take the rotor voltage and I divide it by the rotor impedance, I'm going to get the current flow through the rotor. And what else I could get is the power factor of the rotor. So the power factor of the rotor would be equal to the resistance of the rotor divided by the impedance of the rotor. So at that point in time, the resistance is fixed, but the impedance is changing as it starts to accelerate due to its reactance changing. And I can also get the I active current, or the in-phase current of that rotor. Now that's pretty important current for this rotor. It's basically what's creating the torque in the motor. So the torque of a motor is directly proportional to that in-phase or active current. And to get that, I would just take the I of the rotor and times it by my power factor. So we can calculate this. And rotor frequency, well, that's directly proportional to whatever percent slip we're at. So directly proportional to the percent slip. So what is percent slip? Well, percent slip is if we take our slip speed, or our rotor slip. And what's the rotor slip again? Well, the rotor slip is the difference between the synchronous speed and the actual speed of the rotor. So the difference is between the two speeds. So we take our slip speed and we divide it by synchronous speed times 100. And that'll give us our percent slip that we're at. So what does this look like? Right now, the rotor is not moving, and our magnetic field is at synchronous. It's at synchronous speed. Whatever speed that is moving is the synchronous speed of that motor, based off the number of poles and the frequency of the stator. And so right now we'd be at maximum induced voltage. And so also at this point, it'd be its maximum frequency. Therefore, we'd be also having maximum inductive reactance. The resistance is unchanged. As this rotor starts to accelerate, well, now the percent slip is decreasing. So at blocked rotor, we're at 100% slip. And now that the percent slip is changing, because the rotor is starting to accelerate, our voltage starts getting reduced, our reactance gets reduced, our impedance starts to reduce, our current will come down, and our frequency will also start to come down. And we can see that as it catches up, all those variables that are directly proportional to the percent slip are going to start to get adjusted to the percent slip. This one is also proportional to the percent slip. All right, so having a look here, let's what's really going to help make sense is once we get through something called a rotor chart. And that's what we're going to do next. We're going to look at a rotor chart. So in our case here, we're going to have a 60 Hertz motor. It's a 4-pole motor. And so we could calculate its synchronous speed. Frequency of 60 times 120 divided by a 4-pole motor. So 4. Synchronous speed is 1800 RPM. All right. So I'm going to fill out the top of this rotor chart. And your ILM goes through this in the opposite way. It goes from no load to blocked rotor. I like to start at blocked rotor values and then work our way, or at the moment of startup, blocked rotor, and work our way all the way up to a no load speed. And we're going to look at each one of these different rotor parameters as it starts to change, or as the rotor starts to accelerate. So I put the formulas to calculate each one of these columns. And we're going to start off at 100% slip. And usually in these types of questions, it's going to give you some values. In our question here, it gives us what's the induced voltage at blocked rotor. So that's at its maximum when we block it, or at the moment of startup. The resistance is 2 ohms. Well, that stays fixed based on the composition of those rotor bars. And then the XL is also at maximum. That's when the maximum induced frequency will be there. It'll be at 10 ohms at blocked rotor, or at the moment of startup. And that XL is going to change as the rotor starts to accelerate. So we say it's at 100% slip. What does that mean? Well, that means that the rotor is not moving at all. So the slip is the full 1800 RPM. The rotor voltage at 100% slip, that is the blocked rotor voltage. So we can fill that in. It's 600 volts. The resistance is constant. It's 2 ohms. And the XL, we can also put at 100% slip. The XL blocked rotor is at 100% slip. Now, to figure out what the impedance of the rotor is, well, it's just like making a little impedance triangle. R is on the horizontal, XL is on the vertical, and Z is the hypotenuse. So all we got to use is Pythagorean theorem here. R squared, which is 2 ohms, plus 10 squared, and square root it. At this moment in time, at 100% slip, the impedance of our rotor is 10.2 ohms. The power factor can also be determined with our impedance triangle, R over Z. So if I take my R divided by my impedance at this moment in time, I can get the power factor. So 2 divided by 10.2, about 0.1961. Not a very good power factor. The I of the rotor, we have enough information to figure that out too by using Ohm's law. We take our voltage of our rotor, and in this case it's at 100%, so blocked rotor, and divide it by the impedance of our rotor at 100% slip, or blocked rotor. So 600 divided by 10.2 current in the rotor is 58.82 amps right now. So if we had to convert this over to a current triangle, well, we know the power factor is 0.1961. The I of the rotor, basically the I total of the rotor, is 58.82. So if I multiply my I of my rotor times my power factor, I'll get the in-phase component. So I of rotor multiplied by power factor, 11.53. That's our active current in our rotor. The frequency, well, the rotor's not moving. And the supply frequency, or the primary from the stator, just like the primary of a transformer, it will induce the full 60 Hertz on the secondary, which is our rotor. So that's how we complete the first line on our rotor chart. Let's go ahead and try this out at 75% slip, and let's see what values it affects as this rotor starts to increase. So first off, we're going to determine our slip speed, or our slip RPM. So if you remember, our percent slip would be equal to slip divided by synchronous, and sync. Okay, so if I want to know what the slip is, all I do is multiply my synchronous speed times my percent slip. What's my synchronous speed? 1800. 1800 times 0.75 is 1350. The rotor RPM, well, that would be taking your synchronous speed and subtracting off your slip. That's 450 RPM. If we add the two together, it's got to equal our synchronous speed. All right. So 1350 plus 450 is the synchronous speed. What would be our rotor voltage? Well, it's not cutting. The flux lines are not cutting this rotor as fast anymore. The rotor's starting to catch up a little bit. So the rotor voltage is directly proportional to our percent slip. So E blocked rotor times a percent slip. 0.75 times 600, 450 volts as the rotor's at 75% slip, or 450 RPM. The resistance, well, that stays fixed. That is where it is. It doesn't change on a squirrel cage induction motor. The XL of the rotor, it changes. It's proportional to the percent slip as well. XL blocked rotor, or 100% slip XL, times whatever percent we're at. So 75% of 10 ohms, 7.5 ohms. The impedance of the rotor, R squared plus XL squared square root, 7.76 ohms. Power factor, R divided by Z. So right now the rotor is running at a 0.2577 power factor. The current flow through the rotor at 75% slip. Well, my voltage is 450 now, divided by the impedance of the rotor of 7.76 ohms, 57.99 amps. The in-phase component, well, we take the total rotor current, multiply it by the power factor, we've got our in-phase current in the rotor, 14.94 amps. And the frequency of the rotor, well, it's going to be at 75% of 60 Hertz, so 45 Hertz. Let's try another one here. 50%. Well, 50% slip, 50% times our synchronous of 1800 gives us 900 RPM slip. So the rotor must be going the rest of the 900, because the slip is the difference between the synchronous and the rotor speed. Voltage of the rotor, 50% of 600 volts is 300 volts. Resistance of the rotor stays constant. The XL of the rotor, well, 50% of 10 ohms is 5 ohms. Impedance of the rotor, using Pythag, 2 squared plus 5 squared, square root it, 5.39 ohms. Power factor, 2. Resistance divided by impedance of 5.39, 0.3711. I of rotor, well, that'd be our 300 volts. That's the voltage induced at this point in time, divided by our impedance of 5.39, 55.66 amps. In phase component, I have rotor times power factor, 20.65 amp. Rotor frequency, 30 hertz. So 60% times 50. All right, let's try another one at 25%. I'm just going to put the numbers up here. I think you're starting to get the hang of what we're doing here. And it's a good idea to go through these whole charts and fill them out yourself and do them all. We've got a rotor exercise, rotor table exercise in Blackboard. Feel free to go through that. It'll help you out a lot to solidify this information here. Now we're going to take, you see that it's kind of going 50%, 25%. We're taking a little stutter step here at 20% because something unique happens here at 20%. Now 20% is just within a range. What's about to happen here is something called breakdown torque. Now it doesn't, 20% is just for this motor. It could be in a wide variety of places, anywhere from 25, 30, somewhere in there, percent slip. I'll tell you what is consistent though here when we get to it here. Well, at 20% slip, we are looking about slip RPM of 360 on this motor, 1440 RPM. Rotor voltage will be around 120. The rotor resistance is at 2 ohms. And if we go 20% times 10, the XL is also 2 ohms. What is consistent is when we're at breakdown torque, the R and the XL of the rotor are the same value. All right, and so if we go ahead and Pythag that, 2 squared plus 2 squared square root, we got an impedance of the rotor. And so we can then figure out our power factor, 2 divided by 2.83, 0.707. We have a 45-degree impedance triangle. So this is the point where the motor is going to reach its maximum torque that it can reach. And we call this point the breakdown torque. All right. And so we're going to keep looking a little closer at what's happening with this as we go through. And it's really our in-phase component here that is directly related to our torque. So I, the rotor, okay, well, our reduced voltage is 120 divided by Z. We're at 42.4 amps. And then the in-phase component, 42.4 times 0.707, 29.98. Still going up here, the in-phase component. Frequency, around 12 hertz. Now we're going to look at where we'll operate a motor. And this is just approximate. It's around 2 to 5% slip. So in this case, we're going to say that this in our motor, 2% is the full load RPM. So what does that put our slip at? 2% times 1800 sync, 36 slip at full load. The rotor RPM, 1764. So that'd be about its full load speed. That's what you'd see on the nameplate. Rotor voltage, 2% of 600, 12 volts. Resistance is still fixed. XL of the rotor, well, 2% of 10 ohms, 0.2 ohms. Okay, so we see the XL just keeps going down as it speeds up. It's directly proportional to our percent slip. Z of the rotor, 2 squared plus 0.2 squared square root, 2.01. Power factor, R of rotor, 2 ohms, divided by the Z of rotor, 2.01. We're at 0.995. I of rotor, 12 volts, divided by the Z of rotor, 2.01 ohms. 5.97 amps. In-phase component of that 5.97 amps, well, times that by 0.995. Our active current, or in-phase current, is 5.94, and frequency 1.2 hertz. So that'd be around where we'd operate the motor, about our full load. Let's say if we took the load off now, and so we just let that motor freewheel, we'd be at no load speed. So for our motor here, we're going to say it's approximately 1%. Okay, different for every motor. So 1% of our 1800 sync is 18 RPM. The no load, 1782 RPM. The voltage, well, not a lot of induced voltage, 6 volts. Resistance is still 2 ohms. XL, 1% of 10, 0.1 ohms. Z, 2.002 ohms. Power factor, 0.9988. I of rotor, well, that'd be our 6 volts divided by 2.002, I should say. Z, about 2.997 amps. In-phase component, I of rotor times power factor, 2.993, and around 0.6 of a hertz frequency. So this is a complete rotor chart. And so what we're going to have a quick little look at this and just look at some of the stuff that's going on. So if we notice the power factor of, well, let's start with the Z here. Okay, we see that the Z keeps on declining, right? The voltage keeps on declining. The Z keeps on declining as it accelerates. Resistance stays the same. XL keeps declining. When we go over to power factor, it keeps on getting bigger, so the phase angle is getting better. The eye of the rotor, well, it starts out at its maximum at the point we press our start button, so it's at a standstill or locked rotor, and it accelerates. As it accelerates, the current in the rotor keeps dropping. All right. Well, if we look at the in-phase component of that current, or active, we get a little bit difference going on here. It starts off not too small, but only at 11 amps here, and it is increasing until we reach breakdown torque, and then it starts to decrease again. All right. So when our rotor power factor is at 0.707, we're at the peak of that motor's torque. And if we were to graph this I active, we're going to see something like this. And it's very similar if we were to look at a torque chart for a motor. Now, different rotors are designed differently. Their resistances are differently. Their reactances are different. And what that'll tell us is how this motor is going to perform. We're going to need different torque levels for different types of load. So if we're starting a load that is a variable torque, like a fan, we don't really need a really high starting torque. The torque is required as that fan would accelerate. But other loads, like really heavy weighted loads or high inertial loads, we might need a really high torque at the beginning of it. All right. And so one of the things you guys are going to look at next is you're going to be looking at different rotor designs. And you're going to see why they perform kind of the way what this rotor chart would say, or we could figure out how that motor is going to perform based on their rotor design. So let's keep on going here. Yeah, maximum torque, in this case, it's about 20%. The real thing to remember is that the power factor of the rotor is 0.707 at breakdown torque. The R and the XL will be equal at 0.707. So if we look at a chart basically of our active current or our torque, we'd see that in this rotor, a torque would starts right here, and it increases to its maximum, and then it drops off. Well, we operate this motor in this small range right here. Okay, so a motor can never reach synchronous speed, not a SCIM anyways, not a squirrel cage induction motor. So it always has to have a little bit of slip in order to induce a voltage and create that torque. It needs to rotate the rotor. So this is a blow up over here on the right hand side. So running it at 1/3 of its horsepower or load, we're going to be running it right around here. 2/3, we're going to run it about there. At full load, well, we're going to operate the motor about right there. As soon as we go past full load, we start overloading it. Okay, and so that would be right about right here that we're looking at it. Oh, and so if the overloads didn't trip out at this point, we could continue loading this motor up, and it's going to continue to try to produce that torque that it needs to move the load until we get to this peak torque. If we reach that peak torque by loading that motor up too much, we will stall that motor and lock that rotor up. And then it's basically like having a short-circuited transformer. That rotor is not moving at all. And we're going to have a huge high current flow through the primary, through the stator windings. Chances are, if that breaker doesn't trip, that motor is going to burn up. There will be way too much current and way too much heat going through it. That motor would have to be inactivated as soon as possible. So, and sometimes it's hard to trip those breakers. We size overcurrent for motors quite high, 250, 300%, stuff like that of their full load amperage, which would be sustained. That much current flow for too long would definitely burn it up. So yeah, so what's going on in the induction motor? So that's all I'm going to have in this video. There'll be a video coming out just to talk about wound rotor motors, and I'm going to do some practice examples up next for you guys on working with the rotor chart and figuring out some different rotor parameters. So we'll see you on the next video.